Hi, we're Imogen and Oliver from Polymetis apps. Welcome to our talk, How We Did It, AI, Privacy, and GPUs in the browser. This talk is about our entry to this year's Code Guys competition, how it works, and what we learned along the way. And hopefully, if we do well today, you'll walk out away from this video today knowing a bit more, or at least be a bit more inspired to do more with AI. So anyway, what did we do? We created a secure privacy-first AI-based recommendation engine for Confluence, and we called them Erica. Erica is, of course, a drop pair, and a totally trustworthy drop pair at that. Let's look at what Erica does. There's two main features. Erica allows you to see a personal feed of recommendations, either available on the Confluence homepage or as a macro. Basically, you can think of it as an Instagram or Facebook feed, a social media style feed for your Confluence of pages that have recently been updated and that may be of interest to you. Erica helps you also if you want to find people who might be interested in the content you create in Confluence with the Find Collaborators or Share with Erica feature. And they will suggest a number of users that are most likely to interact with your content. So what do we have in store for you today? First, Imogen will give you an overview of how we think about privacy and security and why we make the trade-offs that we do, not just with Erica, but with all of our apps at Polymetis. Next, I'll take you on a deep dive on how we built Erica and how they actually work. And finally, Imogen will spill the beans on all the steps we had to take along the way before we landed on what became Erica. Frankly, we don't want anyone to repeat our mistakes and to make life easier for you guys. So with that, Imogen?
Yeah. So at Polymetis apps, we have always prioritized privacy. Since I started working at Polymetis in 2019, we have been making most of our apps using Forge for this very reason. So we felt that it would only be natural that at least one of the apps that we submit for Code Guys this year would focus on privacy within the context of AI. Our prioritization of privacy could be seen in the way that we implement a client side machine learning model. We ensure user autonomy, and we are transparent with our users on which data we use to train our model. Yeah, so we decided to run and train our model in the browser to try and minimize the sharing of user data. Typically, apps like ours would use a third party service such as OpenAI. We decided to keep everything on platform so that we would be 100% sure that no data ever leaves our customers' sites. Yeah, as you can see, we don't even use any Forge functions. Oliver will go into more detail on this later, but and put simply, we just communicate between the user's browser where our model is trained and later used, and Confluence's API, where it gets all the pages. And once model is trained, it is saved as an attachment to a Confluence page. Companies such as banks or virtually anything in the healthcare sector often don't want any third party services accessing certain Confluence instances. We wanted to make a we wanted to make something where companies like these could still benefit from modern AI technologies without having to worry if their information might be leaked. In terms of user autonomy, we decided to not let our app fully decide on each step of the recommendations process and give it a human in the loop approach. This can be seen in how we get Erica to give the user three suggestions on who they should invite as a collaborator rather than making this decision on their behalf. We felt that doing this might be too intrusive to our users, and we wanted to give them the autonomy to make this decision. This would be beneficial in our app in certain use cases, such as if an HR representative creates a page containing a surprise for an employee's birthday. But since these two employees communicate a lot, the app could think that this would be something this other employee would be interested in. But due to this being a secret, the HR representative doesn't want it to be shared just yet. So, yeah, we wanted to make something where this would the HR representative could decide when to reveal this information. There are many other examples where this would be extremely important and not just irritating, like in our use case, such as preventing your application from making ethically questionable decisions. Yeah, by offering our users some control over certain decisions in the app, we feel that this might result in a smoother and more harmonious integration of AI into our apps. Lastly, we want to be completely transparent on which information we use for our model and how it has been trained. To do this, we upload each space's model as an extension to a page called Erica's AI Model by Polymetis Apps, where the user can then download it and inspect it. In addition to this, we also include a table on this page which gives certain information about the model, such as the model size, the training time, the error rate, and things like that. And this is mainly for users who have no clue what a model even is. Yeah, so we did all of this because we really wanted to instill a sense of trust in our users. And yeah, Oliver, do you want to show us how it all works?
Sure. So how does it all work? There's a short version or a short answer to this question, and it's a feed-forward neural network doing multi-label classifications that we train on your Confluence data, and it all runs in the browser. And I understand that's a mouthful, so let's look at it in detail. So it's a feed-forward neural network. It basically means we are doing a neural network. A feed-forward neural network is just a specific type, and it is a relatively simple machine learning method at that. It's relatively easy to train it, and we use it to do classification, basically applying one or more labels to an input. In our case, a label would be a user that might be interested to it, and we train a neural network to take Confluence pages and say, this page, this user, this page, that user. And finally, we run everything in the browser. And that is the really fun part here. We train the model in the browser. We do the predictions in the browser. No data ever goes anywhere else. So neural networks are a great tool for classification. And they're relatively easy to understand, at least up to a point. They consist of an input layer that's green here. They consist of an output layer, that's the grayish thing at the end, and one or more hidden layers in between. And the way it works is you give a neural network number inputs. It does a lot of calculations in the hidden layers, and then at the end, the output layers produce some more numbers, which is great. And just figuring out what kind of hidden layer you need, that's basically the training part of the model. And once you've got that figured out, once you've trained the model, you can then use that to apply these classifications. However, neural networks have one problem, and that is they only use number inputs and outputs. That's a bit of a problem because Confluence famously is more about text on pages. So we have to turn these pages into arrays of numbers, and not just that, these have to be consistent number arrays. There's multiple ways to do that. We tried the super simple approach first, the bag of words, basically counting the occurrences of each single word. And then we created a dictionary of all the words we encountered, and we created large vector where each element would correspond to one of the words in our dictionaries, and we would just count how often they appear. This works, but it produces super large input vectors. In the end, we decided to use something called embeddings and a library called the Universal Sentence Encoder, which we got from TensorFlow.js. It works consistently, and it gave us pretty great results. It's not perfect in any way, and it's not really meant for complete pages, as in we are having those in Confluence. It's more meant for sentences, but it does work quite well in our use case. And again, it's very consistent. So we picked it. Once we were able to vectorize the text, we decided, let's get our data. And we opted to do one model per space. To Then we have our training data. So what we do, we get all the pages on the Confluence page. In the Confluence space, we turn them into plain text and turn that text into our input vectors using the sentence encoder. And as output, we ask for any user who's ever interacted with the page, authored it, commented on it, or watched the page. Basically, whatever kind of interaction we find, we take that as the output. And now we have our training data. Input data being the vectors and output data being the users. And it's worth noting that all of the training data that we use in these steps comes from Confluence itself. The models we are building are extremely customized, and they are extremely customized to the specific space we are training on. That means that we don't need super long training times compared to more generalized models. So the bigger the space and the more interaction, the better the model will be. All right, training the model. We're using brain.js, and it's surprisingly easy. It just takes a while. Basically, what you do is you create a new neural network, and then you feed it training data and train it. 2 lines of code. It also is very compute heavy, and there's no way we can fit a decent sized model and a set of training data into the 25-second invocation runtime limit we have in Forge, or the 55-second if we put it on a queue. Forge invocations are just not the way to go here. What do we have to do? We moved this part to the browser. Thankfully, it's 2023, browsers and CPUs are pretty fast, like amazingly fast. Not quite fast enough, though. Training with 500 pages or mid-sized test space, it could easily take 30 minutes on a 8-core i9 Intel CPU and not much less on an M1 Pro Mac. So what else can we do? And here the fun begins. Because GPUs are amazing. They really are. And there's one in every computer now. Even a laptop comes with a really great GPU. And we moved every training there. And training time dropped from 30 minutes to roughly a minute if you've got a good GPU. The library we use, brain.js, is not only easy to use and super flexible, it also has GPU support out of the box. Let's look at what this looks like in like numbers and differences. So this is the Mac Pro I was presenting with, and you can see different spaces and what's the training time in milliseconds. Blue being trained on the CPU and grayish being trained on the GPU. Now, this is nice and interesting, and this is like a good improvement. But just to give you an idea how much better a great GPU can be and how much more of a difference it can make, let's look at an i9 with an actual dedicated GPU on it. And here you can see it's like a 5 times or 6 times improvement in training time. So that's a lot of performance you gain by putting stuff into the GPU. It ought to be really hard to do that, right? Surprisingly, no. To enable GPU support, you just enter, like you just add 3 characters. Instead of saying neural network, you say neural network GPU, and that's it. And since we now reduced the training time from 30 minutes to like a minute or even under a minute, the whole thing becomes much more approachable. And it's still, everything runs in the browser. So to reiterate on this, everything, every data you have stays either within Confluence, in green here, or within the user's browser, in yellowish here. At no point does any data ever go to the Forge platform or even the open internet. It just stays where it should be, in the browser where the user is interacting with it, or in Confluence itself where it's stored. There's no leakage here whatsoever. Finally, once a model is trained, we auto-store it. Models are typically between 2 and 4 megabytes of JSON, extremely readable. It's not super large, but it's not quite right for Forge storage. So we decided to just create a new page in Confluence and attach the model as a JSON there, which has a big bonus of allowing our users to inspect the model and to look at how it all works. As a side note on security, with the kind of model we're using, the feed-forward neural network, it's not really possible to extract the training data from the model itself. So there's no leakage in the model file of any sensitive data, even if it was trained on sensitive data. With an LLM, there might be a theoretically approach there, and it might be possible, but this is not it. Feed-forward networks don't work that way, and your sensitive data is saved and it's not persisted in the model at all. Now, finally, we need to run the model. Whenever we want to make a prediction, hey, who might be interested in a page, we also need to do that. And that is even simpler. It's just one line. We say, hey, let results net run and give it the input data. So we get a prediction. These predictions are basically just an Atlassian account ID, which represents the user, and the resulting number, which is the likelihood that somebody is interested in. It's a number between 0 and 1. It's not a percentage. It's really more dimensionless. But nevertheless, it really does give you an idea. And in this example here, Max Power would be super interested in the page, and Dr. Jen Etor would not be interested at all. And yeah, that's that. Finally, let's talk a bit about model quality and model performance. We obviously want everything to go fast. If training freezes up your laptop for hours or takes really long, or if getting recommendations from Erica takes ages, people won't use that. Like, we have to be fast. If the recommendations are crap and Erica consistently recommends the wrong pages to the wrong users, nobody will care and nobody will use the model. So again, quality is also important. And there is a trade-off here. To get more performance, it's pretty easy. Less data, faster GPU, maybe some caching. But that's how we get more performance. And how do we get better quality? Well, we get better quality with more data. And here it is. Here's the big trade-off. Performance means less data to crunch. Quality means more data to crunch. We did not quite find a way out of this, but we found that this is not the whole picture, because it's not more data, it's more meaningful data. So the best way to approach this trade-off is to improve data quality. That means have a better signal to noise ratio in our data. We currently do this by removing stop words and removing pages with very little text. Depending on what you know about the data you're training on, you could also try other inputs like topic extraction. Learn what kind of topics and themes a user is interested in and try to find out what page is about what topic. And with that, Imogen, what did we learn?
Yeah, so I think it's safe to say that we learned a whole lot in the process of making Erica. So we thought we would share our journey and some of our key insights. So some of our team members had done some work in machine learning, but as a front end developer, I had to learn everything from scratch. Shortly before this code geist was announced, I was given the task to research browser side machine learning so that we could implement it into a few of our current apps. So I started this process where I think a lot of people do, which is by completing the Coursera course by Andrew Ng on machine learning. And this really helped with my overall understanding of this field. I think it's safe to say that Andrew Ng is just really great at explaining everything step by step. I then stumbled upon a library called ML5JS, which is essentially built on top of TensorFlow.js, and it makes it really easy to work with machine learning models with everything being written in JavaScript. It was there that I was introduced to the coding train by Dan Schisman. And for anyone who is remotely interested in getting into browser side machine learning, I would definitely recommend watching his videos. I've never come across another instructor who is so enthusiastic about what they're doing, and it's just really great at explaining everything step by step. They also have a whole lot of pre-made models, which easily help you do amazing things such as image content recognition, human pose estimation, and many more. As we honed down on what we wanted to actually do for our code guide submission, it was made clear that we really needed to vectorize our Confluence pages. And unfortunately, their Word to Vec feature is not available. So we decided to go back to TensorFlow.js once again. Working with TensorFlow.js turned out to be too complex for what we had in mind, especially when building a model from scratch. However, we found that their ready-made model, universal sentence encoder, was extremely useful. And as Oliver mentioned before, it was great at vectorizing our Confluence pages, which we then fed into a neural network we created in brain.js. Brain.js is similar to ML5JS and turned out to be a better fit for our specific needs, but I would definitely recommend looking into ML5JS first and working with their pre-made models, and then looking into brain.js. Yeah, both are really easy to use and understand. So the main challenge that we faced with client-side machine learning is that it's still pretty new in comparison to server-side machine learning, and there are just not as many pre-made models built for it. The pre-made model we used worked really well for our core guide submission, but if we decide to make Erica one of our marketplace apps, we would definitely have to use a different model. TensorFlow.js uses a light version of the universal sentence encoder due to computation resources being limited for browser-side models. This version only supports English, and being a company based in Europe, we really need our apps to accommodate a variety of languages. But as you can see, machine learning has become very accessible, and the fact that there are machine learning libraries written in JavaScript means that even more people can reap the benefits of it. Yeah, there are a lot of resources out there on this topic, which can make getting into it a bit overwhelming and send you down a variety of rabbit holes. But having colleagues who keep you on track is really essential in finding the best tools out there. To sum everything up, we ultimately feel that there is a lot of value in client side machine learning. It obviously can't do as much as some of the big, large language models can. But for smaller use cases like ours, it can provide users with a safe way to optimize their workflow. Libraries such as ML5, JS, and brain.js are making it much easier to get into machine learning. All you really need is a great GPU. And lastly, I think it's safe to say that machine learning and the development of AI is here to stay, and that we can all benefit from these technologies immensely. If we implement it in a safe way that does not compromise our users and their privacy, then hopefully it will remain a positive influence in all our lives. Yeah. Thank you.
Thank you all for listening. It's been a pleasure. And let us know if you built anything fun and interesting.